Good morning, everybody. Welcome to our statistics class. We're going to talk about descriptive statistic number 4 today, which we call measures of position. So we actually covered 1, frequency distributions, those distributional counts. 2, central tendency. 3, measures of dispersion, the degree to which our data points are spread out from each other. Number 4 is measures of position, which is really a study of percentile rank. Now what we're doing here actually in this study of the measure of position is really looking at a topic called standardization. Standardization. Standardization is a set of procedures in which we transform, and that's the key word here, we transform raw scores, like test scores, your heights, any list of data are considered raw scores. We transform raw scores to another scale. And that other scale has a known mean and standard deviation for the purpose of determining percentile rank. And we're going to spend about an hour or so and see how this is all done. We're actually going to see how the big boys do it. In studying measures of position and standardization, what we're really doing here is taking a good hard look at what we call the standard normal distribution. The standard normal distribution. And you guys are familiar with the normal distribution. And again, this is covered in Chapter 3 and really in detail in Chapter 6. But you guys are pretty familiar with the characteristics of this normal distribution. We have this bell-shaped curve. We have this bell-shaped curve with a midpoint. A midpoint that splits the distribution right in half. And we also know that in the normal distribution, remember the mean, median, and mode are all identical. The mean, median, and mode are all identical. So we could put mu here. And we know that about 50% of the distribution, 50% of the scores fall from this position back. We know that the median is the 50th percentile. 50% of the area or 50% of the scores fall from here back. Like I said the other day, many distributions out there in the real world, in the scientific world, are indeed normal. Many of them look like this. In fact, scientists actually use this normal distribution to describe many naturally occurring events. One of the most widely used standard scores, out there in science is what we're going to be working on this morning. That's the z-score. That's the z-score. Now z, per se, is the distance from the mean It's the distance from the mean to any score in a distribution in standard deviation units. Ranging from -3 to +3 with a mean of 0 and a standard deviation of 1. The z-score is the distance from the mean to any score in a distribution in standard deviation units, ranging from -3 to +3, with a mean of 0 and a standard deviation of 1. So on our standard normal distribution here, we can put 0 right in the middle. And we can actually partition this curve just like you see it done in the book. We partition this curve into these segments, so to speak. And we can draw these areas, these percentages, 34.13%, 34.13%, 13.59%, 13.59%, 2.15%, 2.15%. These percentages we call areas under the curve. The z-scale ranges from -3 to +3, ranges from -3 to +3, with a mean of 0 and a standard deviation of 1. So you see each z unit is 1 unit. 1 unit. These percentages, like I said, are areas. So just very simply, about 34.13% of the area is between a z of 0 and 1. If we add these numbers up, if we add this plus this plus this, it's about 50%. 2.15% of the area under the standard normal distribution falls between a z of -2 and -3. Very small percentage. If we add this plus this plus this plus this plus this plus this, we get about 100%. Actually a little bit less than 100%, because these tails are called asymptotes, and theoretically they go off into infinity. They never touch this horizontal axis. Now you'll see in your textbook that they do something like this. They just add these areas together. They add this plus this. Constitutes about 68.26% of the area under the standard normal distribution. If we add this area plus this area plus this plus this, we get about 95% of the area under the standard normal distribution falls between a z of +2 and -2. And if we add, again, this plus this plus this plus this plus this plus this, we get a little bit less than 99%. I'm just going to put a little bit less than 100%. I'm just going to put 99+%. So we're going to be working with these areas a lot this semester. We'll be working with them today in our determination of percentile rank, descriptive stat number 4, but we're going to be seeing this a lot. We'll be seeing it a lot. The most widely used standard score is z. Now formulaically, there's another $7 word, formula. Z is expressed a couple different ways. score minus mean over standard deviation. Score minus mean over standard deviation. Or we see it expressed like this. Score minus mean over standard deviation. We see it expressed in population context or sample context, just depending on what type of arena we're working in. Let's see how this all works in making determinations of percentile ranks. Let's suppose we have a population. Let's suppose we have a large N of like 10 million college students. Just imagine a large N of 10 million college students. We got a ton, we got a very large population of college students. Capital N is like 10 million. Let's suppose, and just write this down, let's suppose that given a normal distribution, let's suppose that given a normal distribution of these 10 million scores, with a population mean equal to 36, comma, and a population standard deviation equal to 5, comma, we randomly select five scores. We randomly select small n equals 5 scores. Now, let's just stop for a second. We have this standard normal distribution. We have a population mean of 36. We have a population mean of 36 and a population standard deviation of 5. Do you remember the other day I said S or sigma is equal to 1 z unit? Well, now we're going to learn what that really means. We have a sigma of 5. We have a population standard deviation of 5. We're going to go out addition-wise this way, back subtraction-wise this way. 36 plus 5, 41. 41 plus 5, 46. 46 plus 5, 51. 36 minus 5, 31. 31 minus 5, 26. 26 minus 5, 21. We have a raw score scale, and we have z-scale. Yeah. This is telling us now that in terms of these 10 million kids that took the test, kids just like you, the actual range was from 21 to 51. About 68.26% of this population actually scored between 31 and 41. A very small percentage scored between 21 and 26, and so on. About 34.13% of the kids who took this test scored between 36 and 41. So imagine 10 million scores, all these little data points. We got 5 million scores from here all the way to here, right? 5 million scores from here all the way to here. So actually the 50th percentile, which is the median, is right here. It's also the mean, right? It's also the mode. It's the most frequently occurring score. So, 10 million scores, mean 36, standard deviation 5. We randomly select a really teeny little sample of 5 scores. Our scores look like this, 5 of them. And we're going to call them X. 42, 34, 45, 40, 32. Our job now is to determine where does each one of these scores fall in relation to all the other scores, all the other people who took the test. All the 10 million kids who took the test. Where do these particular scores fall in relation to all the others? Well, again, it's really important to keep it simple. Keep it simple. Look, let's start with this. This 42. Let's just visualize. Where does this 42 fall on this distribution?
42.
How did this kid do in relation to all the others?
Good.
Pretty well. How about the score of 32 down at the bottom? How did this kid do in relation to all the others? Not so great. Let's compute Z and percentile rank. We're just going to say, what are the Z scores and percentile ranks? So we'll create a little column for Z, and then we'll convert to percentile ranks. And you're going to have to get your books out, turn to the front covers of your textbooks, to the table of the standard normal distribution, turn to the table of the standard normal distribution. Yeah, there you go. That's T.
It's on the inside.
It's on the
Okay.
other side.
Okay.
Yeah, open that up.
Everybody turn to the Z table, which is the table of the standard normal distribution. And let's get started. We're going to be using this formula. We're going to convert raw score to Z score for the purpose of determining percentile rank. Let's do that. For the raw score 42, Z is the score, 42, minus the mean, 36, over the standard deviation, 5. That looks like 6 over 5, or a Z of positive 1.2. A Z of positive 1.2. Oh, it's right here. Look, it corresponds, it lines right up with that raw score 42. Our job now is to determine the percentile rank. That's the area from here back. That's the area from this position back this way. You're going to see me doing a lot of this today. The area from here back. Everybody go to a Z of 1.2 in your tables. And there's a number there. It's actually a proportion. Tell me what that is. Go to a Z of positive 1.2 and tell me what that is. 0.8849. Or the 88.49 percentile. I just converted a proportion to a percentage. This is actually not a percentage per se, it's the percent area. It's the percent area from here, this position, back this way. What this is saying, class, is that this kid who scored a 42 actually scored better than about 88.5% of the people who took the test. Pretty good. Pretty good. Now, you guys are all really smart. You're all really bright. So you answer this question for me right now. This raw score 34, when you look at the standard normal over there, is Z going to be positive or negative? Negative. Negative. Very good. Now the question is, how negative? Well, let's see. Z is the score, 34, minus the mean, 36, over the standard deviation, 5. This looks like negative 2 over 5, or a Z of negative 0.4. Negative 0.4. It's about right here. Lines up with the raw score 34, right? Our job is to determine percentile rank. That's the area from this position, right, back this way. Go to a Z of negative 0.4 in your tables, and there's a proportion there. Tell me what it is.
0.3446.
0.3446, or the 34.46 percentile. This kid, who scored 34 for a raw score, scored better than about 34.5% of the people who took the test. So about 2/3 of that 10 million actually did better than him. Let's try it again. Class, this raw score 45, is Z going to be positive or negative? Positive. Yeah, 45 is right here. He actually did pretty well. Yeah. Let's take a look at this. Z is the score, 45, minus the mean, 36, over the standard deviation, 5. This looks like 9 over 5, or a Z of positive 0.8. A Z of positive 0.8. Z is right here. Our job is to determine percentile rank. That's the area from here back. Everybody go to a Z of positive 0.8 and tell me what the proportion is. That's the area from that particular position back to the left. That's how it explains it to you. What is that number? 0.9641. Oh my gosh, I did. Z is 1.8. Thank you very much. Z is 1.8. That is right here. Everybody go to a Z of 1.8. And we have this on film. This is great. Go to a Z of 1.8. Tell me what the proportion is.
That's correct.
0.9641, or the 96.41 percentile. This particular student who scored 45 actually did better than about 96.5% of the kids who took the test. Pretty good. Pretty good. He actually scored in the top 5%. The score of 40, is Z going to be positive or negative? Yeah, now our job is to determine just how positive. Let's make that determination. Z is the score, 40, minus the mean, 36, over the standard deviation, 5. That looks like 4 over 5, or our Z of 0.8. I got a little ahead of myself there. Z is right here. Percentile rank, area from here back. Everybody go to a Z of 0.8. Tell me what that proportion is. What is that number? 0.7881. Or the 78.81 percentile. This student who scored a 40 scored better than about 78.81% of the people who took the test. Not too bad. And finally, for the raw score 32, class, is Z going to be positive or negative? Negative. Did this student do very well? I don't think so. So all you have to do is just keep this stuff out in front of you, just kind of like a ground ball, you know. Keep it out in front of you, and it pretty much will tell you in a real general way what we're doing, and then we can just get real specific by saying Z is the score, 32, minus the mean, 36, or the standard deviation, 5. This looks like negative 4 over 5, right? Or a Z of negative 0.8. A Z of negative 0.8. We're about right here. Our job is to determine percentile rank. Again, that's area from here back. Everybody go to a Z of negative 0.8. There's a number there. It's a proportion. Tell me what it is. 0.2119, or the 21.19 percentile. This student didn't do real well. The score of 32 only scored better than a little bit more than 21% of the people who took the test. And again, these percentiles, in this case, this one, this number, about 21.19% of the area under the standard distribution, standard normal distribution, falls from this point back this way. Falls from the Z of negative 0.8 back this way. So there are areas from some position back this way. The percentage of individuals, you know, at or below a certain point on a distribution.
So even if someone scored 51, it won't be 100%?
Yeah, the 51 would be at like the 99.999th percentile, so to speak. Yeah. Yeah. Okay. Very quickly, class, draw another standard normal distribution. Just a little bit down in your notes, please. You do it pretty quickly. It doesn't have to be a work of art. Just do it real quickly. Draw the z-scale. Maybe draw the areas under the curve. And in your notes, write this. We can use z-scores to compare many different measures. That have different means and standard deviations. We can use z-scores to compare many different measures that have different means and standard deviations. You notice I'm using these symbols now, assuming that you guys know what this stuff means. Different means and standard deviations. It converts them to a common scale. it converts them to a common scale. Let's suppose we have a typical IRSC student, IRSC college student, and she's got 4 classes this semester. Probably, maybe working part-time, maybe working full-time, whatever. She has 4 classes, and she has an econ class. She also has a class in accounting. She's got a bio class, and she's got a class in linguistics. Linguistics. Does anybody know what linguistics is? Yeah, it's a study of language. The characteristics of languages in terms of sounds and phonemes and all this. It's pretty hard course. Pretty hard course. Well, about 3-4 weeks goes by in her semester, right? And her professors in these 4 courses decide they're going to give the first midterm, just like we do. Ours is coming up in a little while. I'll talk about that later. But she takes her first 4 exams, and her professors decide that they're going to compute a class mean, right, and a class standard deviation, in terms of the tests. And then our student has her score. Well, as it turns out, in the econ class, the mean was 56 with a standard deviation of 5. Our student scored a 50. Now everybody look, is this score above or below the mean, guys? Below. So is their Z going to be positive or negative? Negative. So did she do real well compared to her classmates? No. It's obvious. It's right there. Right there. You guys are doing really well, by the way. You're picking this up. That's good. For accounting, the class mean was 47 with a standard deviation of 3. Our kids scored a 55. Class, that score of 55, is it above or below the mean? Above. It's above. Did she score pretty well or not too pretty well? She did pretty good. Yeah, look at how far above the mean this score of 55 is. Remember, we're going out in units of 3 in terms of Z in this particular case. She did pretty doggone well. For bio, the class mean was 63 with a standard deviation of 7. So in this case, 1 Z unit equals 7. Our kids scored a 70. How well did our kid do well or not so well? I think she did pretty well. Yeah. This is definitely above the mean of 63. And finally, in linguistics, the class mean was 53 with a standard deviation of 4. Our kid scored a 43. How did she do in linguistics? Not so good. Look at how far below that mean is. Now, I have a class. I have a question for you, class. I have a question for you guys. Compared to all her other classmates, on which test did she do the highest? On which test did she score the highest? And on which test did she score the lowest?
Accounting.
Now, some of you actually were able to, get this pretty quickly. Others, you know what? It's not so easy. Let's compute Z and percentile rank, and it's going to make things a lot easier. And we're actually going to be using this form of our z formula because these are what our givens are. So let's do this. Let's start with economics. Let's compute z. We're going to say z is the score, in this case 50, minus the mean, 56, over the standard deviation, 5. This looks like negative 6 over 5, or a z of negative 1.2. Z is negative 1.2. Z is right here. Everybody go to a z of negative 1.2 in your z tables, please. And tell me what that number is. 0.11. 0.1151. Move the decimal over. It's the 11.51 percentile. She only scored better than about 11.5% of the people who took the econ test. Not so great. Not so great. Let's try accounting. Let's convert the raw score to the z-score for the purpose of determining percentile rank. Okay, z is her score, 55, minus the mean, 47, over the standard deviation, 3. It looks like 8 over 3, right? Or a z of positive 2.6. Z is way over here. Percentile rank, area from here back. It's going to be quite high. Somebody go to a z of positive 2.6. Tell me what that proportion is. 0.99, what? 53, or the 99.53 percentile. Pretty good. In fact, she scored better than about 99.5% of the people in her class. You know, I think she might have got the highest grade in the whole accounting class. Bio. Mean 63, standard deviation 7. Her score, she scored a 70. Let's convert to z. Z is her score, 70, minus the mean, 63, over the standard deviation, 7. This looks like 7 over 7, or a z of 1. Z is right here. Everybody go to a z of positive 1.0. Tell me what that area is. 0.8413, or the 84.13 percentile. Our kid actually scored better than about 84.13% of the people who took the bio test. This is a good teaching moment here. We have a z of 1. I can actually erase this because it doesn't apply. We have a z of 1. 84.13% of the area falls from here back. Look, 50% plus 34.13% equals 84.13%. All we did was add 50% to this particular area right here to get the percentage area under the curve from this position back this way. It's kind of easy to see. Now, of course, if z was like 0.68, it would not be easy to see. We'd have to go to the tables. But in this particular case, this is pretty easy to see that it's the 84.13 percentile. 50% plus this particular area is 84.13. Finally, for linguistics, we know she didn't do real well. Let's take a look. Z is her score, 43, minus the mean, 53, over the standard deviation 4. This looks like negative 10 over 4, or a z of negative 2.5. We're right about here. Not real good. Somebody go to a z of negative 2.5. Tell me what the number is.
0062.
0.0062, or the 0.62 percentile. I think she got the lowest in her whole class in linguistics. Now, when I ask you the question, it becomes a lot clearer as to what the answer is. When I ask you the question, class, compared to all her classmates, on what exam did she score the highest, and on what exam did she score the lowest? It's obvious now, and some of you got this correct. It's obvious that she scored the highest on accounting because she has the highest percentile rank, and she scored the lowest on linguistics because this is the lowest percentile rank. Measures of position. Looking for that particular position where the percentage of scores falls at or below. Okay, take a minute, draw another standard normal distribution, please. Do it very quickly. Doesn't have to be a work of art. I'd like to talk about a couple of other very widely used standard scales. You guys are familiar. How many of you took the SAT? How many took the SAT? Okay, all right. We have a standard scale called SAT. Mean 500, standard deviation 100. Mean 500, standard deviation 100. So we have a mean of 500, standard deviation 100. 500, 600, 700, 800, 400, 300, 200. SAT scale. Mean of 500, standard deviation 100. Now this tells us something. This tells us that, you know, about 68.26% of the people who take the SAT score between 400 and 600. You know, a very small percentage score above 700. It's a very small percentage. So what is considered normal, SAT, is right in here. This is the most normal. It's the highest frequency. You know, the majority of the scores are 500 on the SAT. We have another very widely used standard scale called IQ, the Wechsler IQ test. We all know what IQ is. Supposedly a measure of intelligence. Really, all this is a score on a test. That's what it really is. It's a score on a test. Regardless, mean 100, standard deviation 16. Mean 100, standard deviation 16. So we just do the drill here. 100 plus 16, 116. Plus 16, 132. Plus 16, 148. 100 minus 16, 84. Minus 16, 68. Minus 16, 52. We have another standard scale called IQ, mean 100, standard deviation 16. Again, this tells us something. This is a standard normal distribution. It's telling us what's normal. It's telling us what the norm is. The norm, when you hear that term, the norm, it's mu. It's what's considered normal. Normal intelligence is considered a score of 100. The most frequently occurring score on the Wechsler IQ is 100. But you know, about 34.13% of the people who take the test score between 100 and 116. You know, very small percentage of people who take the Wechsler IQ score above 132. A really, really small percentage score above 145. I think they're called Mensa, right? A very small percentage. But again, you know, it's just a score on a test. And what is that really? It's the ability to, you know, figure out the right answer. But let's suppose we take the SAT and we get our scores back and we get, you know, a 516 on the verbal. And right next to that score, we're given a percentile rank. Well, this is how they did it. Real simple. Z is the score, 516, minus the mean over the standard deviation. That looks like 16 over 100, or a Z of positive 0.16. Z of positive 0.16. And you see that positive 0.16 lines right up with 516, a little bit over 500. Somebody go look at a Z of positive 0.16. Tell me what that proportion is.
0.9452.
No, that's not correct.
0.5636.
0.5636. Or the 56.36 percentile. So what this is telling us is that this score of 516 actually scored better than about 56.5% of the people who took the test. Just a little bit beyond that 50th percentile, which is the median, right? And the what SAT score class would constitute the 50th percentile? 500, yeah, that's the median. Let's suppose we get our results back, and on the quantitative portion of the SAT, we get a score of 496. Is Z going to be positive or negative, guys?
Negative.
Yeah. Well, let's just see how it goes. Z is the score, 496, minus the mean, over the standard deviation. This looks like 4 over 100, or a Z of negative 0.04. Somebody go to a Z of negative 0.04. Tell me what that area is.
3446.
Point what?
3446.
No, that's not correct.
I was going to say 0.4480.
A Z of 0.04.
It's 0.3447.
That's 0.4. You got 0.04.
Yeah, 0.04. 4443. Or the 44.43 percentile. So this score of 496 only scored better than about 44.43% of the people who took the test. Okay, let's do this again. Let's suppose we take the Wechsler IQ. Let's suppose, okay, let's suppose this gentleman here takes the Wechsler IQ, and he scores a 126. What's the z-score in percentile rank? Let's take a look at it. This is how they figure it out. Z is the score, 126, minus the mean, or the standard deviation. This looks like 26 over 16, or a z of what? 1.65. Positive 1.65.
6.3. It'll be 3.
6.3. Okay. Tell me that proportion. What is it?
0.9484.
0.9484. Or the 94.84 percentile. What this is telling us is that this gentleman right here who scored 126 on the Wechsler IQ actually scored better than about 94.5% of the people who took the test. Okay. Measures of position, percentile rank. In your inboxes on Angel, there's a set of homework problems. It's sitting in there right now. And it's identical to the exercise that we did the very first thing. If there's a little story problem, it lists the population mean, population standard deviation. It gives you a set of scores, and I want you to convert those to z-scores and then percentile rank exactly like we did in our exercises this morning. That will conclude our lecture this morning on measures of position.